Hi guys, we are back with another reading of our chemistry review from the Barron's review course series. We have gotten up to section 1.4 in chapter 1. So we are going to continue with the metric prefixes. So very often, an SI unit is not convenient for expressing measurements. For example, the meter is not useful for describing the diameter of a red blood cell or the distance between Earth and the Sun. There are two ways to deal with this dilemma. We can use scientific notation, which is introduced in the next section, or we can use metric prefixes to create multiples and subdivisions of any unit of measure. The accompanying table lists some metric prefixes along with their symbols and values. We saw this in a past section here when they mentioned it. I had pointed it out, so now you get to see it again. We have a factor of 10 to the 15, which is peta, symbol capital P, factor 0.1. P symbol, sorry. The 0.1 is deci, which is symbol D, but let's go in order. So 10 to the 15 is peta, capital P. 10 to the 12 is tera, capital T. 10 to the 9th is giga, capital G. 10 to the 6 is mega, capital M. 1,000 is kilo, small k. 100 is hecto, small h. 10 is deca, symbol DA. Factor of 0.1 is deci, symbol small d. Factor 0.01, prefix centi, symbol C. Factor 10 to the negative 6 to the negative 6, prefix micro, symbol is mu. 10 to the 9th factor, prefix is nano, symbol is N. Factor 10 to the negative 12, prefix pica, symbol small p. And factor 10 to the negative 15th, prefix femto, symbol lowercase f. For example, we use the term picogram, pg, to designate 10 to the negative 12 gram, 1/trillionth of a gram. This is a very small quantity of matter. An abbreviated list of metric prefixes appear in reference table C in Appendix 1, so that's in the back of the book. Section 1.5, Scientific Notation. Once we have established a system of measurement, we need to be able to express small and large numbers easily. Scientific notation accomplishes this purpose. In scientific notation, a number is expressed as a power of 10 and takes the following form: 10 to the 10 raised to the n. M times 10 to the n, or 10 raised to the n. Again, capital M times 10 raised to the lowercase n. M is called mantissa, and n is the exponent. So this is what they're referring to. It's m times 10 to the lowercase n. Let's see if I can focus it. Nope, no, that's as good as we get. Okay, so the mantissa is a real number that is larger than or equal to 1 and is less than 10. 1 is less than or greater to m, less than 10. The exponent is an integer that can be positive, negative, or 0. For example, the number 2,300 is written in scientific notation as 2.3 times 10 to the third, not as 23 times 10 to the second, or 0.23 times 10 to the fourth. The number 0.0000578 is written as 5.78 times 10 to the negative 5. To write a number in scientific notation, we move the decimal place until the mantissa is a number between 1 and 10. If we move the decimal place to the left, the exponent is positive. So this is the left, right? So if we move it this way, it's positive. If we move the decimal place to the right, this is the right, the exponent is a negative. So if you go 1, 2, 3, that's negative. To multiply two numbers expressed in scientific notation, we multiply the mantissa and add the exponents. The final result must always be expressed in proper scientific notations. Here are two examples. So let's see if you can see this. I don't know if it's going to... Okay, it's relatively clear. Those are the examples, so you can pause it. Pause the video and actually look at those examples. Division is accomplished by dividing the mantissa and subtracting the exponents. To add and subtract two numbers expressed in scientific notation, both numbers must have the same exponent. The mantissa are then added or subtracted. The following examples illustrate the application of this rule. So here are the examples, relatively clear. Okay, so every calculator is different. Become familiar with how to input and manipulate scientific notation on your calculator. Doing so will help you work with classifications involving scientific notations. Now for section 1.6, volume and density. In addition to the functional or fundamental metric quantities, there are many derived quantities that are combinations of the fundamental ones. So in addition to the fundamental metric quantities, there are many derived quantities that are combinations of the fundamental ones. For example, the speed of an object is the ratio of the distance, length, it travels to a given amount of time. In chemistry, two derived quantities are of immediate interest to us, volume and density. So volume. The volume of an object is the amount of three-dimensional space the object occupies. The SI unit of volume is a cubic meter, m cubed. The SI unit of volume is a cubic meter, m cubed, or m raised to the third, which is too large for particle use in chemistry. We will use the cubic centimeter, cm raised to the third, or cm cubed, which is approximately equal to 1/100th of a quarter, and the liter, which is approximately equal to 1/4. 1 liter is equally or exactly equal to 1,000 cubic centimeters. We often designate 1/1000th of a liter as a milliliter, ml. It follows that 1 cubic centimeter equals 1 milliliter. So we often designate 1/1000th of a liter as a milliliter. It follows that 1 cubic centimeter equals 1 milliliter. So we had said 1 liter equals 1,000 cubic centimeters. So 1 milliliter equals 1 cubic centimeters. Now density. Density is the ratio of mass to volume. And here is the equation there. Symbolically, this is written as follows. Density equal mass over volume. Density measures the compactness of a substance. A substance such as lead has a large density because a relatively small volume of lead has a relatively large mass. A substance such as styrofoam, the material used to make coffee cups, has a small density because a relatively large volume of styrofoam has a relatively small mass. Density is a property that depends only on the nature of a substance, not on the size of any particular sample of the substance. For example, A solid gold coin and a solid gold brick have very different masses and volumes, but they have the same density because both are pure gold. Again, density is a property that depends only on the nature of a substance, not on the size of a particular sample of the substance. For example, a solid gold coin and a solid gold brick have very different masses and volumes, right? Because a solid gold coin and a solid gold brick, they have, where am I? Different masses and volumes because they're different sizes, but they have the same density because both are pure gold. In the SI system, the unit of density is the kilogram per cubic meter. In chemistry, the densities of solids and liquids are commonly reported in grams per cubic centimeter, while the densities of gases are given in grams per cubic centimeters, or equivalently in grams per liter. We will solve some problems involving density in section 1.8. Again, in the SI system, the unit of density is a kilogram per cubic meter. In chemistry, the densities of solids and liquids are commonly reported in grams per cubic centimeter, while the densities of gases are given in grams per cubic decimeters, or equivalently in grams per liter. Next, we have section 1.7, reporting measured quantities. Every scientific discipline, including chemistry, is concerned with making measurements. Since no instrument is perfect, a degree of uncertainty is associated with every measurement. In a well-designed experiment, however, the uncertainty of